Okay, class, so we are now continuing section 9.5. Last time we talked about equations of lines, and now we talk about equations of planes. And in section 9.5, on the section on planes, it mentions that although a line in space is determined by point and direction, a plane in space is more difficult to describe. Okay, a single vector parallel to a plane is not enough to convey the direction of a plane, but a vector perpendicular to the plane does completely specify its direction. One moment, class. Okay, thank you, everybody. Okay, so um, basically, in a nutshell here, what they're saying. Let me just remove this. Okay, so a plane in space is, I'm sorry, I don't know why this phone keeps ringing, class. One moment. Okay, again, I apologize about that. Let's keep going. So a plane in space is determined normally, like you've probably heard that a line in space or a line is determined by 2 points. And a plane, so 2 points uniquely determine a line, 3 points uniquely determine a plane. How many have heard of that, like before, maybe in pre-calculus or back in high school? How many of you have heard of that? Sure, Brand recalls that, and Alexander recalls that, Norina and Simon, and but we can look at a plane in another way. If we knew a point on a plane and we had an orthogonal vector to the plane, a vector that's perpendicular to the plane, that would also uniquely determine the plane. The orthogonal vector n is called the normal vector. So to see a picture of this, look here at figure 6. Okay, see here? You have a plane that contains a actual point, p sub 0, and there's a normal vector to the plane, and that also uniquely determines a plane. So if we can find a point on the plane and a vector perpendicular to the plane, that will uniquely determine the plane. And based on this, we can come up with an equation of a plane. So you see here in the picture, on the plane, you have actually 2 points. You have a p sub 0 point, and then another point, p. And then you have the normal vector to the plane. And then from the origin, you have 2 position vectors, vectors r and r sub 0, that are drawn out to those 2 points on the plane. And then if you take r, the vector r minus r sub 0, that's that blue vector which lies in the plane. Okay, so let's make sure that you're comfortable with this in figure 6. Do you see how the blue vector, which is the difference of the vectors r and r sub 0, do you see how that blue vector must lie in the plane? And that vector is perpendicular to the normal vector to the plane. Do you see that reasonably well? Okay, very good, Yeva. By the way, what can you tell me about the dot product between that blue vector, r minus r sub 0, and the normal vector? What's true about the dot product? What must it equal? Since those 2 vectors are perpendicular, That's right, Lexi. Very good. 0. That's right, Angela. That's right, Mary. So the dot product between that red normal vector and the blue vector, r minus r0 in the plane, equals 0. And it's actually based on this equation that I have highlighted, that you can come up with the equation of the plane. You see, if you have let me see here. Let me just show you this on the whiteboard. So if you have this dot product equal to 0, remember the dot product is distributive. So with the rules for the dot product back in section 9.3, this dot product would imply that this equation is true, because the dot product distributes. Okay, so it distributes. Notice that I have the dot product distributes. These are dots here. So this means that n dotted with the vector r, wait, hold on, this is a 0, right? Let me just slow down a little bit here. Yeah, n dotted with the vector r equals the dot product of the vector and r sub 0. Now the vector n has components, say, A, B, C. That orthogonal vector to the plane has components A, B, C. If you remember the figure, the vector r had components x, y, and z. And so and the vector r sub 0 had components x sub 0, y sub 0, and z sub 0. So now what we're trying to do is we're trying to find out what the equation of a plane is. Well, okay, if we look here on the left and do the dot product, we're going to have ax plus by plus cz equals, and then on the right, we're going to have a sub x0 plus b times y sub 0 plus c times z sub 0. And you see how this is going to yield then a times x minus x sub 0 plus b times y minus y sub 0. Hold on. Let me make sure here. One moment here, class. I got to check something. Yeah, that's right. Plus c times z minus z sub 0. That would all equal 0. In other words, this is the standard form for equation of a plane. And it just comes from subtracting on the equation above. If you subtract the right side over to the left side and then factor A, B, and C, you will get this equation down here. You will get that equation down there. And so now we have derived, using multivariable calculus, we've derived the We've derived the equation of a plane. How many have seen that maybe in pre-calculus when you learned about planes and they just said, okay, this is this, like, I don't know if you've seen this standard form for the equation of a plane. Maybe you have not. Maybe you have not. But let me show you something. Let me show you something. Let me go back to the whiteboard here. Okay, let me just show you something. So here we are. We have a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equals 0. And on the left, we can write this as ax minus ax sub 0 plus by minus by sub 0 plus cz minus c times z sub 0 equals 0. Just going to take my time here. And then we can go a little further and write this as ax plus by plus cz equals then a times x sub 0 plus b times y sub 0 plus c times c sub 0, right? We absolutely can do that. Now, let me just double check here, one moment. And this here, we can call, that's some constant d, because a, x sub 0, b, y sub 0, c, c sub 0, 0, those are specific numbers. So you get this equation of the plane, ax plus by plus cz equals d. How many have maybe seen that in pre-calculus for the equation of a plane? Something like this. Yeah, Simon recalls that. Simon recalls that. Now, if you wanted, by the way, if you wanted to call this negative d, then you could rewrite this as, if you just wanted to call this, you know, a times x 0 plus b times y 0 plus c times z 0, just call it negative d. I mean, it's negative some d value d. We could add that over, and then this is probably more familiar to you, the equation of a plane, ax plus by plus cz plus d equals 0. That's probably more familiar. Okay, so are there any questions? Any questions on this? All right, let's see if we can, let's see here. Yeah, I'm gonna look at an example in the book, and then I have another example I'd like to do. So let's try to work through those. Let me go back to the book here. Well, now where's the book? Hold on, let's try it again. Oh, here it is. Okay. So a plane through 3 points. Here, sorry, let me get it here. We want to find an equation of a plane that passes through 3 particular points. So they give 3 points, and if we wanted a nice little picture of this, we could look at figure 8. So let me just show you here, figure 8. There's the plane. Now, in figure 8, of course, they're not drawing the whole plane. The whole plane goes on forever. They're just drawing a portion of the plane. And whenever you have 2 points, well, we have 3 points, okay? We have 3 points. But, and that, of course, uniquely determines the plane, but we don't have the equation of the plane. So to get the equation of a plane, we need 1 point on the plane, which we have. We actually have 3 points in this example 5. But what else do we need regarding the plane? To find the equation of the plane, what else do we need to find in addition to that? Okay, that's right, Yeva. We need a normal vector to the plane. We need a vector that's perpendicular to the plane. Okay, so can we find 2 vectors in the plane? Can we find the vector PQ and the vector PR? Could we could we find those 2 blue vectors? They lie in the plane. The vectors PQ and PR, they lie in the plane. Can we find them? How would we find the vector PQ? What would we have to do with the points?
Subtract.
Good, R. You'd have to subtract the points. So we could find the vector PQ and we could find the vector PR by subtracting the points. And once we have those 2 vectors that lie in the plane, what are we going to do to those 2 vectors to get the orthogonal vector to the plane? What operation? Good, Norina. We have to do the cross product. So you learned that when you take the cross product of any 2 vectors, and any 2 vectors are going to lie in a plane. When you take the cross product of those 2 vectors, you're going to get a vector that's perpendicular to the plane. And that's what we need. Okay, so are there any questions so far before we go and look at the solution? Okay, well, let's go then. So here, the P and Q, they compute them. They subtract the points, and they call them vectors A and B. And then they do the cross product. They do the cross product of those 2 vectors to get the normal vector to the plane. So a normal vector to the plane is 12i plus 20j plus 14k. Now all you have to do, now that you have the normal vector to the plane and you have a point on the plane, all you have to do now is utilize this equation here. So in this equation, which is the equation of a plane, the A, B, and C are components of the orthogonal vector, and x sub 0, y sub 0, and z sub 0 are the coordinates of a point in the plane. So we just substitute in the values for A, B, and C, and the values for x sub 0, y sub 0, z sub 0. That's all we do. And so when we do that, see, that's what they did. So hopefully, again, what they're doing is they are using the point 132. Let me see here. One moment. There was a question. Yeah, I mean, let me see. So Lexi's asking about the points PQ and PR. All right, let me see here. So you're thinking the book's not right on that? All right, let me. So we're here. Yeah, a question was asked about the previous homeworks. Not an error. I deactivate the previous homeworks during our lecture time because I want you to listen to the lecture. So let's take a look here. Hold on. I get worried when I have intelligent students that don't agree. All right. So I'll tell you what. Let's just we'll verify those vectors. But do you all see at least? No problem, Christina. No problem. Do you all see? Then what they do is they you know, do the algebra, and they write that equation in simplified form as 6x plus 10y plus 7z equals 50. That's the equation of the plane. Okay, that's the equation of the plane. Now let me just see here. I want to let me just do it on paper here. What Lexi and a few other students are asking about is well, actually, hold on. I can bring it up on the whiteboard. For this example 5, so the vector A, they're calling PQ. So I don't know why this phone keeps ringing. All right, just keep. All right. Gosh darn it. All right. What I have, class, I'll tell you the problem. See, home I live in, there's a landline phone here that actually my brother wants to keep, and I can't, like, you know, it's not like my cell phone where I can put it on. Well, hey, maybe I can silence that. Maybe I'll try to do that, but let's not worry about that now. So what we're doing is we're verifying the vectors A and B from example 5. So let's see, 3 minus 1, negative 1 minus 3. And 6 minus 2. And we get the vectors 2, negative 4, and 4. Yeah, that checks out. That's vector A. Unless I have an error here. Hold on. No, no. So I'm looking in example 5. So for my example 5, the point P is 1, 3, and 2, and the point Q is 3. So there's a typo in the book. Okay, thank you, everybody. Typo in the ebook, everybody, for example 5. For example 5, point P should be 1, 3, 2, Q should be 3, negative 1, 6, and point R should be 5, 2, 0. So A is PQ, B is PR, and if you work out PR, you will get 4, -1, and -2. Good catch, Lexi and others who caught that. So occasionally there are going to be typos in the book. I mean, that's surprising that the ebook would have that. But at any rate, okay. Who has it in their ebooks? I mean, the ebook should be the same for everybody. Is that typo? So it's the first one, right? In example 5, the 132. That I mean, in Lexi, you have that, or you have that. Okay, okay. All right, that's interesting. Okay, well, at least we clarified that, and very good, very good. All right, let's look at one more example here. I'd like to do one more before we take a break. Let me see here. Hold on. Okay, let's take a look at this problem. Now, this problem is, the book has many good examples. This is an additional one just to give you extra examples. Let me give you a moment to copy this example down. Okay, so this problem, what we want to do is we want to find parametric equations for the line that passes through the point 510, but that is perpendicular to this plane. And then we want to know at what points does the line intersect the coordinate planes. Okay. Now, these kind of problems in section 9.5, what might be helpful to get our minds thinking? Because we have to know what to do here. We have to know what to do. What might be helpful to have to get us thinking? This is a geometric problem. It would be nice to have a
diagram.
That's right. Absolutely. That's right, Aura. We need a diagram. So what I'm going to do here is I'm going to draw a plane. And this, let's see, we know the plane passes through the point 510. Do we know the orthogonal vector to the plane? I mean, they give the equation of the plane. Okay, there it is. So what's the normal vector to the plane going to be? What would its components be? Good, Ashish. 2, -1, and 1. Because those are the coefficients. Those are the coefficients of x. You know, there's -1 here, y, and z. There's a 1 there, right? So there you go. Okay, so let's draw a little picture here. So I just drew a plane, you know, a plane. Now, one thing on this plane that should be here is, let me just see here. This is not the origin. Okay. I mean, basically, the vector 2, -1, 1. I mean, let's say this plane does not pass through the origin. Okay, it does not pass through the origin. But let's say that the origin were here. It's just a sketch. And this vector had components 2, -1, 1. Well, that vector could be just, you know, that vector is orthogonal to the plane. So, you know, that's why I have this right angle here, and there's the vector. Vectors determined by direction and magnitude. This vector and this vector, these two vectors have the same direction and the same length. So I can just take this vector here, drawn from the origin, and put it right on my picture of my plane. And it is perpendicular to that plane. But also the plane has on it, let me just see here, the plane, hold on. The plane passes through the point 5, 1, 0. But this also is a little bit, let me just see here. So this line here is perpendicular to the plane, hence the right angle. But, and I'm going to have to, I guess, fix this. This 510 shouldn't be there because it's like, looks like it's on the plane. 510 is not on the plane because if 2 times 5 minus 1 plus 0 is not equal to 1. So 510 is like off of the plane. Okay, so I'm going to have to fix that in my notes here. You know, we want our picture to be, it's just a sketch. It's just a sketch, but it gets us thinking, right? It gets us thinking. So, okay, so now what we want to do is we want to find the parametric equations of the line. Well, we know what direction that this line L here, we know what direction, maybe I can, kind of like highlighting things, you know. I mean, here's our line L. We know what direction it goes in, and we have a point on the line. So you learned then that we can come up with the parametric equations to the line. So the vector r, which is the vector equation of the line, equals r sub 0, which is the point on the line, plus t times a vector v. The direction the vector line goes in is the vector that had the direction vector is 2, negative 1, 1. So this gives us then our parametric equations. And so parametric equations for this line are given by x equals 5 plus 2t, y equals 1 minus 1t, and z equals 1t. Those are the parametric equations for the line. Now, please let me know if there are any questions so far. All right. Let me ask you this: could these three parametric equations here, x equals 5 plus 4t, y equals 1 minus 2t, and z equals 2t, could they also be parametric equations for the line? They could, or they could. Because these three other parametric equations, well, that's right, Lexi. Those parametric equations are for a line that passes through the point 510, but is parallel to the vector, I'll write it here, 4, negative 2, and 2. Now, for the other parametric equations of the line, that line passes through the point 510 as well, and is parallel to the vector 2, negative 1, 1. But the vector, I like to put it in different colors, the vector 4, negative 2, 2 here is parallel to the vector 2, negative 1, 1 here. So both of those parametric equations describe a line that passes through the point 510 and goes in the direction of the vector 2, negative 1, 1. Okay. Whether you say the line passes through the point 510 and is parallel to the vector 2, negative 1, 1, or the line passes through the point 510 and is parallel to the vector 4, negative 2, 2, those two lines are the same line. That's what I'm saying. Give me a thumbs up if you're good so far. I want to make sure people are good, comfortable. Wonderful, wonderful. All right, all right. Well, and I might take a moment to mention, you notice how by staying, excellent Brand, you notice how doing the homework that was due today is helping you understand these concepts. Excellent, excellent. All right, Alexander, and there was another person, thank you. Let me see here, I like to try to, Simon, very good, excellent. Shifa, Sadhana, Christopher, wonderful. Now we want to know, now that we know we can describe our line with the parametric equations, and I think I will utilize these ones since, they're just a little easier. Now we want to know where the line intersects, at what points does this line intersect the coordinate planes? So let's see. Let's talk about the coordinate plane the XY plane. Okay, the coordinate plane. So here, just go to the whiteboard. So here's our line. With these parametric equations. So, right. And when does this line, and when I say when, I really mean for what value of t? For what value of t does this line pass through the XY plane? So for what value of t does this line pass through the XY plane? So as t changes values, it gives you different points in space, and collectively all these points trace out a line in space. But for one particular value of t, and this line, it's not a horizontal line; it's a skew line. So for one particular value of t, this line is going to pass through the XY plane. Now, what's another way of saying XY plane? How can we write the XY plane as an equation? That's right. Good, Yeva. Z equals 0. Okay, so can we figure out then, given that these are our parametric equations, and that we're requiring a z to equal 0, because it's the line will pass through the XY plane. When it does that, the z coordinate has to equal 0. Can we figure out what t is? Can we figure out what t is? What t would have to be? For what value of t? So to figure out the value of t, we have to focus on the equations that have t in them. That's right, Alberto. Very good. T equals 0, because based on the third equation, z equals 0 plus 1t. So if 0, then, we need 0. Z equals 0. If 0 equals 0 plus 1 times t, this means that t must equal 0. So what we're going to do then is take that value of t and substitute it in the other two equations to determine x and y to get our coordinate. So if I go back to the problem itself, okay, if I go back to the problem itself, then here's what we're saying then. So the line intersects the line intersects the XY plane for a value of t that satisfies these equations. But the third equation, which parametric equation, which was z equals 1 times t, well, that has to be then Z has to equal 0. So this means t is 0, and we figure out that x is 5 and y equals 1. So this line L intersects the xy plane at the point 5, 1, 0. That has to be where the intersection is. Now, if we want to know where the line intersects the YZ plane, well, the YZ plane can be written as x equals 0. So now we set the first parametric equation equal to 0. And based on that, if 0 equals 5 plus 2t, then negative 5, let me just go ahead and hold on. Negative 5 equals 2t, so therefore negative 5 halves equals t. And so that's what gets substituted in here, in those other two parametric equations, and that gives us our y and z coordinates. So the line L intersects the YZ plane at the points 0, 7 halves, and negative 5 halves. Are there any questions on this? Okay. Well, then to the very last one, I didn't work through for you, but you can show that the line L intersects the XC plane at the point 701. Okay, I'll let you show that. Who's feeling good about this problem? Are we okay? I mean, are you understanding what we're doing here? Okay, R is good, wonderful. Simon and Devasina are good. Marina, wonderful, wonderful. Are there any questions? Okay, good, good. So what I'm going to do, we're going to look at a few more problems dealing with planes from section 9.5, but that'll be in a new recording. Let me go ahead and stop this recording here.